Picture this. You're standing on the 150th floor of the Burj Khalifa, nearly half a mile above the ground, and you flush a toilet. That waste has to travel down 163 floors through a vertical drop equivalent to stacking 5 statues of liberty on top of each other. By the time it reaches the bottom, it's moving at terrifying speed, fast enough to shatter porcelain, burst pipes, and turn the world's most luxurious building into a sewage disaster zone. And yet, every single day, the Burj Khalifa handles waste from 35,000 people without a single pipe exploding, without a single backup, without a single geyser of sewage erupting into a $4 million penthouse. So, how do they do it? How do you move waste down from the clouds without turning the entire building into a plumbing nightmare? The answer involves physics most engineers never have to think about. Solutions that sound absurd until you realize they're the only thing standing between luxury and catastrophe. And a design so clever that it's now being copied by every super tall skyscraper on Earth. Let's break down the full process. From the moment you flush on floor 150 to the second that waste safely reaches the treatment system below. And see exactly how the world's tallest building solved one of the most dangerous problems in vertical construction. In a normal building, say, 10 or 20 floors, gravity is your friend when it comes to waste disposal. You flush, the waste drops through vertical pipes, called stacks. It picks up speed for a few floors, then it hits the horizontal sewer line at the bottom and flows away. Simple, reliable. Been working for over a century. But the Burj Khalifa isn't a normal meters tall, it's 2,717 feet. That's 163 floors of vertical drop. And when waste starts falling from that height, gravity stops being your friend and becomes a demolition force. Here's what happens if you just let waste freefall from the top floor to the bottom. It accelerates fast. In the Burj Khalifa, wastewater reaches terminal velocity, the maximum speed an object can fall through air, at around 10 to 16 feet per second within the first few floors. From there, it just keeps slamming downward, floor after floor, building momentum, building pressure, building kinetic energy that has to go somewhere when it finally hits the bottom. And when it does hit the bottom, when a column of waste traveling at terminal velocity suddenly has to transition from vertical to horizontal, it does. T just gently curve into the sewer line. It stacks, it surges, it creates something engineers call a hydraulic jump, which is a fancy term for a violent wall of liquid slamming into a pipe that wasn't designed to handle it. If you didn't design for this, here's what happens. The pipes temporarily overfill. Pressure waves shoot back up through the system. Sewer gas seeps into the hallways. Toilets on lower floors gurgle, back up, and in the worst cases, erupt. You'd have sewage geysers blasting out of fixtures on the most expensive floors of the most expensive building on Earth. Game over. So the engineers faced a brutal question. How do you let gravity do its job without letting it destroy the building in the process? The first defense against catastrophic waste flow is surprisingly simple. Make the pipes massive. The Burj Khalifa's main vertical waste pipes, called soil stacks, are roughly 24 inches in diameter. That's 2 feet, wider than a large pizza. Wider than most people's torsos. For comparison, a typical house uses a 4-inch waste pipe. A normal apartment building might use 6 to 8 inches. The Burj Khalifa uses 24 inches. And there's a very specific reason why. When waste falls down a narrow pipe, it fills the entire cross-section. The liquid forms a solid plug that traps air below it. As that plug accelerates, it compresses the air beneath, building pressure that has nowhere to go. Eventually, that pressure blows back upward, forcing sewer gas through every weak point in the system. Drain traps, toilet seals, shower drains. You get the smell, the noise, and eventually, the backup. But when you widen the pipe dramatically, something elegant happens. The falling waste doesn't fill the pipe completely. Instead, it spirals down along the walls in a thin sheet, like water circling a drain. The center of the pipe stays open, forming an air column that allows air pressure to equalize naturally as waste descends. This prevents the plugging effect. It prevents pressure buildup. It prevents the hydraulic shocks that would otherwise turn the system into a ticking time bomb. The waste still falls fast, but it falls in a controlled, predictable way that the pipes can handle. But even with 24-inch pipes, you can't just drop waste straight from floor 163 to the basement. The sheer distance would still create too much momentum, too much pressure, too much kinetic energy slamming into the bottom. So the engineers did something brilliant. They broke the vertical drop into stages, instead of one continuous 828-meter freefall. The Burj Khalifa's waste system uses staged collection points located at strategic intervals throughout the building. Here's how it works. Waste from the upper floors, say floors 120 to 163, drops down through the soil stack until it reaches a collection tank on, for example, floor 120. That tank acts as a buffer. The waste enters, slows down, and pools temporarily. Then it exits through a separate pipe that continues the descent to the next collection point, maybe on floor 80. This process repeats several times as waste moves down the building. Each collection point serves the same purpose: to break the momentum, to give the system a chance to reset, to prevent any single section of pipe from experiencing the full kinetic force of a half-mile drop. Think of it like a staircase versus a slide. If you tried to slide straight down from the top of a skyscraper, you'd hit the bottom at lethal speed. But if you put in landings every 30 floors where you slow down, stop, then continue, you arrive safely. The Burj Khalifa's waste system works the same way, controlled descent, stage by stage, preventing catastrophic velocity buildup. Another critical design feature is the use of horizontal offsets. These are sections where the vertical pipe shifts slightly to one side before continuing downward. The offset forces the falling waste to change direction, which dissipates kinetic energy and prevents it from building up too much speed. Imagine dropping a ball straight down a tube versus dropping it down a tube with a bend every few floors. The bends slow it down. They force the ball to collide with the walls, lose momentum, and continue at a safer speed. The same principle applies to wastewater. Every horizontal offset is a speed bump built into the system, ensuring that by the time waste reaches the bottom, it's traveling at a manageable velocity. These offsets are carefully calculated. Too many, and you risk creating blockages where solid waste gets stuck. Too few, and you don't dissipate enough energy. The Burj Khalifa's engineers used computer simulations and fluid dynamics modeling to find the optimal placement, angle, and frequency of these offsets throughout the building. Here's another problem most people never think about: air pressure. When waste flows down a vertical pipe, it displaces air. If that air has nowhere to go, it creates a vacuum behind the falling waste, which can suck water out of drain traps, the U-shaped pipes under sinks and toilets that prevent sewer gas from entering living spaces. If the drain traps lose their water seals, sewer gas floods into apartments. You get the smell, the health hazard, and very angry tenants. To prevent this, the Burj Khalifa uses an extensive system of vent pipes running parallel to the waste stacks. These vent pipes connect to the soil stacks at regular intervals and extend all the way to the roof, where they open to the atmosphere. As waste falls and displaces air, that air is pushed into the vent pipes and safely exhausted outside. This keeps pressure balanced throughout the system. It prevents vacuums from forming. It keeps drain traps full. It ensures that no matter how much waste is flowing, air can always circulate freely, preventing the pressure shocks that would otherwise tear the system apart. The most dangerous moment in the entire waste disposal process is the transition from vertical to horizontal at the base of the building. This is where all that carefully controlled downward flow suddenly has to change direction by 90 degrees and enter the horizontal sewer line that leads to the treatment plant. If this transition isn't designed correctly, you get a hydraulic jump, a violent collision where fast-moving vertical flow slams into slower horizontal flow, creating a backup that can surge back up the system. The Burj Khalifa solves this with oversized transition chambers. These are large concrete chambers located in the basement where the vertical soil stacks terminate. The chambers are big enough to absorb the incoming flow, slow it down, and allow it to settle before it enters the horizontal sewer pipes. Inside these chambers, the flow transitions gradually. The waste enters at high velocity, spreads out across the chamber floor, loses speed, and then exits through a much larger horizontal pipe that can handle the volume without backing up. It's like a highway on ramp. You don't merge onto the highway at full speed from a dead stop. You use the ramp to accelerate smoothly. The transition chambers work the same way, allowing waste to decelerate smoothly before entering the sewer system. Here's a fact that sounds like a joke but isn't. When the Burj Khalifa opened in January 2010, it wasn't connected to Dubai's municipal sewer system. The city's infrastructure simply hadn't kept pace with the breakneck construction. Dubai was building faster than it could support, and the underground sewer network didn't reach the tower yet. So for the first 3 years of operation, the world's tallest building, a half-mile tower of steel and glass housing some of the wealthiest people on the planet, relied on a fleet of trucks haul its waste across the desert every morning. Orange tanker trucks would pull up to the base of the Burj Khalifa. Workers would connect hoses to underground holding tanks, vacuum out the waste, and drive it miles across the desert to treatment plants that could handle the volume. It was a 163-story marvel of 21st-century engineering, serviced by a 19th-century bucket brigade. This lasted until September 2011, when the city finally completed the sewer connection and the Burj Khalifa could discharge waste the way it was always meant to, underground, through pipes, like a normal building. But for nearly 3 years, the tallest structure humanity had ever built depended on trucks, lots of trucks. It was absurd. It was embarrassing, and it was a reminder that no matter how advanced your skyscraper is, if the city around it isn't ready, you're stuck improvising. The Burj Khalifa's waste system isn't just a fun engineering story, it's a blueprint. Every super-tall skyscraper built since 2010 has studied this system, borrowed from it, improved on it, because the physics don't change. Gravity doesn't care how expensive your building is. If you don't control the descent of waste, the system will fail violently. Right now, towers are rising that will surpass the Burj Khalifa. The Jeddah Tower in Saudi Arabia aims for over 1,000 meters. Other projects are pushing even higher, and every single one of them will face the same challenge. How do you move waste down from the clouds without destroying the building? The solutions will be refinements of what the Burj Khalifa proved works: wider pipes, staged collection points, horizontal offsets, vent systems, oversized transition chambers. The principles are the same. The stakes just keep getting higher. Here's the thing about the Burj Khalifa's waste system. No one sees it. Tourists stand in the observation deck on floor 148 and marvel at the view. Residents sip champagne in penthouses and watch the sunset. Nobody thinks about the 24-inch pipes running through the core, the collection tanks, the vent stacks, the transition chambers in the basement. But without all of that invisible infrastructure, none of the luxury would be possible. You can't have a vertical city without solving the vertical problems, and waste disposal is one of the hardest, most dangerous, most unforgiving problems in super-tall construction. The engineers who designed this system didn't get their names on the building. There's no plaque in the lobby celebrating the genius of staged waste collection. But every time 35,000 people use the facilities without incident, every time a toilet flushes on floor 150 and nothing explodes, that system is working exactly as intended. It's invisible, it's unglamorous, and it's absolutely essential, because the Burj Khalifa isn't just a triumph of architecture, it's a triumph of plumbing. And that might be the most impressive thing about it.